So good evening everyone. We have been discussing on understanding different machines from field perspective, and yes, that last day one interesting question was asked regarding bar current calculation. Can we actually do that from, if we have open source software like FEMM, we can only do magnetostatic. That means we cannot actually give some time varying current, which is some current which is varying in time, and accordingly we cannot look at what happens and how torque gets produced. Basically, because bar current, those are induced, so it depends on rate of change. But in those open source softwares like FEMM, we can only do magnetostatic, and we cannot actually do transient simulations. So I discussed how it could be done with certain approximations. So last day I just explained with hand-drawn things. So I thought that it would be good because it's very interesting. So it would be good to reiterate with some figures before me. So I'll quickly go through that. So suppose uh, we have this machine, whatever I have indicated, I have put on the left hand side, and this is a how many slots machine. This is a 24 slot machine, and 24 slot 2 pole machine, winding made for 2 pole formation. And at this instance, say it is t equal to 0, and you can see that the axis is here and actually the flux direction, as you know, will point rightward direction. So this side is into the stator it's entering, so this side will be south pole and this side will be north pole for the stator. Now we can from magnetostatic simulation, what can we do? We can inject different currents. So we know that current in a particular phase varies sinusoidally. So we can at say instant 1, we know what is the R phase current. Accordingly, if I draw other phase currents also, IR, IY and IB. If I plot other phase currents also, which are phase shifted three phase sinusoidal currents, at this instant, at a given instant, say this instant, we know what is the corresponding IR current, and IY current will be some negative current, and IB current will be the same positive current. So we know at the given instant what are the currents, and at a given instant we know, if we know what are the currents, then we can inject that in magnetostatic simulation and get this type of field plot where flux lines are plotted. And at that instant if we draw a circle in the air gap, and if we look at the, if this is theta equal to 0, then theta equal to 90, theta equal to 180 and theta equal to 270, we can get, if we traverse in this direction, say anti-clockwise direction theta, then we can get what is going to be the this B distribution, radial component of B, the distribution of that along this air gap circle. So we will get this type of a distribution, where you can see at 0 degree it is positive maximum, at 180 degree, if we consider the fundamental sinusoid component of this, then at 180 degree it is the negative of that, and again 360 degree it is the positive peak. So 90 degree and 270 degree it is 0, as can be seen from this flux line plot also. Now say we want to calculate what is going to be the flux linkage at this instant for different rotor bars. So let us we did some nomenclature. So because I am doing it now, it may not be the same, but probably red one I indicated as B1. Then next thing we did is 1 2 3 4 1 2 3 4 5 6 7, so B7, basically 6 slots afterwards. So I'll just take B1, B7 and B13, let us say three bars at this instant. Say it is the t equal to 0 instance, so rotor bar, okay, B7, say it is at theta equal to 0, B1 is at if it is 0 degree, then this has to be 300 degree, because it's 6. Okay, so what is that? How many slots do we have? We have 30 slots on the rotor. Total is 360 degree. So 360 by 30 is 12 degree. So the difference is 1 to 7, that is 6 slots. So the if this is 0 degree, this has to be 6 times 12 degree, that is 72 degree. So 360 minus 72 will be 268 degree. So for B1 at theta equal to, or omega t equal to 0, let us say B1 location we denote by theta 1 is equal to 268 degree. B7, that is at theta 7 is equal to 0 degree, and B13, theta 13 is uh, 0 plus 72, that is 72 degree, right? Accordingly we can do it for all the rotor bars. So we have we have a thing like this. So we are looking at the first instant omega t equal to 0, and we know what is the corresponding so at that instant what are the angle which rotor position or at which angle the different bars of the rotor are located at. Now what we need to calculate the flux linkages. We need to calculate the flux linkage of all the different bars. So bar 1, bar 2, bar 3, bar 4, all the bars we need to calculate. Now for that what we need to do is, because it's a two pole machine, so if we have to calculate the flux linkage of that, we have to take so say we are interested to calculate psi 1. Psi 1 is, what is psi 1? Psi 1 is the flux linking the B1 um, rotor bar. So for calculating that, we have to integrate. We have to integrate the B distribution. So this is B as a function of theta, where this is theta, horizontal axis is theta, this vertical axis is B, and B varies as a function of theta. So you have to take a integration of B over theta. Actually, if I just do that math, this is a cylindrical body. So this is like a cylindrical body. So if we take a small strip of angle d theta, and the rotor radius or the air gap mean radius, say it is r, then this arc length is r into d theta. And if axial depth, that is ls, then the area dA is basically ls into r d theta. Now flux is nothing but what is flux? Flux is nothing but B into dA. So if we are looking, we are at some theta, then it will be B of theta into dA. That is the flux. And dA is, what is dA? B theta. dA is ls into r into d theta. Both ls and r, they are constants, so they can safely be taken out of the integration. So ls into r, those go outside the equation, outside the integration, because they are constants, and we have b theta into d theta, and the integration limits will be uh, whatever is the theta 1. So it will be theta 1 minus pi by 2 to theta 1 plus pi by 2, because it's a two pole, so mechanical angle is same as the electrical angle. So we have to take, so if we have to take calculate the flux linkage of a coil, because one turn, if one turn is at 0 degree, another turn will be at 180 degree. So we can calculate, we can do integration for 0 to 180 degree, right? But in this case, actually what is happening in this case? In this case, we calculate what is the flux linking one conductor, and what is the flux linking another conductor, and we add it up because that is a turn. Now for a conductor we have to do half of that. So instead of total 180 degree, we have to look around that conductor only, and we have to look at. So suppose if I take an example, say some conductor here. What are the flux which what are the flux lines that is linking this conductor? Actually all the flux lines which are all throughout, which start from um, say 180 degree and go to 360 degree or 0 degree. So what are we actually doing? If we are interested to calculate the flux linkage of this coil, then we have to take uh, integration from this whatever is this angle, say it is 90 degree, we have to take integration from 90 degree minus 90 degree to 90 degree plus 90 degree, that is in this case 0 degree to 180 degree. So in a general case, if theta 1 is the location of the conductor at that given instant, then you have to take integration from theta 1 minus pi by 2 to theta 1 plus pi by 2. Right, what does this mean here? If where is our b1 located? B1 is located somewhere here, probably I'll use some other color. So b1 is located at 260 degree, 270 degree basically, probably here. 270 is was my calculation correct? This is 72, this should be 60 plus this should be 88, right? 288, 360 minus 72, that is 288 degree, not 270 degree. So yeah, 288 maybe somewhere here the conductor is located. So you have to go 90 degree before and 90 degree after, and calculate do integration. So you can see that some negative B is there, so it is basically the area enclosed the B curve beneath this region. So that can be calculated. We can calculate and get this psi 1 at omega t equal to 0 degree. So psi 1 can be calculated like this, and similarly psi 2, if I do, this is Ls into R, this remains the same, and whatever we know the this is psi 7 because I have taken B7 bar 7. So it will be theta 7 minus pi by 2 to theta 7 plus pi by 2. So theta b7 is at 0 degree. So you have to take integration from so 0 minus 90 will be 270 degree from here to 90 degree. So you can see that all the positive b is within this range. So this will have the maximum flux linkage, and so is this for b7, uh, b7 b7 the coil location is at 0 degree, so if we take integration, we have to take from minus 90 to 90, uh, from 270, so minus 90 to 90, is it correct? Because all should be positive. B7 B7 should have, as we can see, it should have zero flux linkage. uh, for zero flux linkage, that means we have to uh, no flux line is enclosing this, means uh, where is where is that I am missing? So if it is B7, the flux linkage has to be or how to calculate flux linkage, there probably I have done some mistake here. So in order to calculate flux linkage by that B7 conductor, we have to take integration around that. Mm, so say if this is the conductor and everywhere, yeah, I think there is a mistake in this minus 90 to plus 90, because as you can see for this even 90, because one side will be negative, another side will be positive. So actually for this definition what we have is 0. So yeah, so for flux linkage what do we need to do? We actually need to calculate what is enclosing that conductor. Okay, so how to get back to how to calculate flux linkage, probably I'll think and get back to it. But final thing is you can do some integration over this b theta and get the flux linkage value for all these different instants. So psi 1, so at this given instant, say omega t equal to 0 degree, it is possible. I'll just get back to with these limits, but it is possible to calculate the flux linkage of this particular bar. So psi 7, psi 13, all this can be calculated. So we can plot the flux linkages of all these different bars. Now next, if we after some rotation, say we go to t2, we go to some new time instant, that is t2. So the time angle becomes omega t2. And how is omega t2 related to or we if our rotor speed is say theta, or rotor speed is omega r, then the bar 1, which was earlier at 288 degree, that one will rotate if that is rotating in the anti-clockwise direction. So theta 1 at omega t2, if we look at the different bars, so b1, b7, b13, first at omega t2, first we have to calculate what are the theta, what are the theta values. uh, so all these are basically at omega t equal to 0, and this is the theta, that is the location of the bar. So at omega t2, the angle of a particular bar, say theta I, that we are going to write in this column. So what will be theta 1? Theta 1 will be whatever was theta 1 in the omega t equal to 0 or omega t equal to or t equal to 1 instant, plus whatever is omega r into the time difference, that is t2 minus t1. So we can calculate what is the new theta 1, at t2. So basically theta 1 t2 is theta 1 t1 plus omega r into t2 minus t1. So this different uh, theta 1 at the given at the new instant, so omega t2 instant, that those can be calculated. Similarly b1, b7, b13, all this can be calculated. And at this new instant again we can do magnetostatic simulation and get uh, the b distribution, radial b distribution with theta. And as we know the locations have changed. The magnetic field is rotating at certain speed, so it has rotated by some angle, but the bars have rotated by a different angle. So we have known this different angle at the new instant. Linkages of these different bars, using the taking an integration of b with theta for the limits that I'll come back with. So we know what is the psi of different bars at t2 instant. Now similar things can be done for say a period or two. Then we know we can calculate, we have waveforms of say psi 1, psi 2, similarly psi 30. We have flux linkages waveforms with as a function of time for all the bars. And once we know psi 1 as a function of time, we can differentiate that and get and calculate the induced EMF. So induced EMF can be calculated by d psi dt. So if I put subscript I and subscript I every I for the other case also, then we can calculate the induced EMF like E1, E2 to E30. All these induced EMF can be calculated. So, as we know, induced EMF at different instance, uh, it is possible to calculate the resistance of the bar because it's a solid bar with some resistivity of the resistivity of the material, lengths and cross sectional areas are known. So it can be calculated. Calculate the bar resistance can be calculated, and bar inductance can be estimated by some analytical expression or can be found from magnetostatic simulation itself. So what happens if we inject nothing, neither stator nor rotor, and only inject some one bar with certain current, say 1 ampere, and calculate and get what is the flux linkage of that bar. So inductance, self inductance will be nothing but whatever flux linkage we get divided by current. So this is how we can calculate the bar inductance, basically bar self inductances. So if we model the bar as some RL circuit, we know what is the induced EMF, what is the induced EMF getting applied across that bar from these calculations at different instance, and we can this is a circuit, RL circuit for the bar. So if we know this induced EMF, then the bar current can also be calculated. And once the bar currents are known, then the end ring currents can also be calculated as following the steps that I have indicated in probably two classes before this one. So this is the systematic procedure how only from magnetostatic 2D magnetostatic simulations also we can solve for this transient, or we can get these transient results, basically solve for flux linkages with time, induced EMF, all this can be calculated. So yeah, this is just to elaborate the procedure once more. And as there was some confusion regarding this limit of integration for calculation of flux linkage, I think there is some confusion, so I'll just get back to it in the next class.
Yeah,
So
Samrat ji, just small doubt. It's a
yeah,
basic only. Yeah,
yes,
here now the B radial flux over the angular position we are plotting, right? That is a flux.
yes.
It is a resultant flux or no, actually, if I can see on the rotor and stator structures, so it's a two pole machine. I can see it here. Okay,
Yes, yes.
two pole machine. So in this now, either in in like outward flux is there and inward flux is there, correct? So
Correct,
both
correct.
sides are there. So now
Yes.
like I'm exciting the rotor with exciting the stator,
Yes.
then there is a flux will the flux linkages will come normally, and then
Yes.
once if it is rotor rotating also one more flux linkages will come. So now
Yes.
whatever we are seeing on the rotor side, it is a resultant flux or like an individual flux. If I wanted to see means like how?
So yeah. So actually, what happens is the resultant flux. Okay.
Yeah,
Actually, there is the both excitations are there, and there are
yeah.
the air gap flux density is the resultant flux density, right? But for this
Mhm.
analysis, we cannot. We have to first know what is the current that is getting injected in order to calculate the flux linkages of the rotor bars. So this is the first assumption that that goes in this type of analysis. If we try to do from 2D magnetostatic to, if we try to calculate the bar currents, then the first assumption that we have to take is uh, we will only consider the stator consider the stator induced this flux density distribution in the air gap in order to calculate the rotor flux linkages. Okay, so that is the first assumption, and
Okay.
it is true also. It is not that it is not true, because what we will see for the DC machine what happens if we inject both, and if we try to look at the flux linkage of a certain conductor, then you will see that although the resultant field is looks little different, but actually the resultant flux linkage does not, the value does not change, because we will see, we will see when we go there.
Yeah, just a minute. No, the thing
Yes.
is, I have my stator flux direction and also rotor flux direction also.
Right.
It is like 90 degrees,
90-degree for induction machine in this case, yes.
90 degrees per, apart from each other both. So now,
Yes.
if now what are the whatever I can see on the diagram now in this at this point of time now, between yellow and that blue color, there is a flux direction, either upward or
Yes.
downward. Now, based on my conductor position, correct?
Yes.
That is my rotor.
Sorry.
Is it rotor or stator? Is it rotor flux direction or stator flux direction?
Currently that I am showing is only stator flux. Rotor is not excited
It
in
is,
this case till now.
no, normally earlier cases also, whenever we have seen all the cases with respect to the stator exited only that. Now, whatever we have
Yes, yes,
discussed in the
yes.
last
Whatever
all
we
the
have
classes,
discussed till
all
now
the.
is only one flux excited. Like if I go back, say
Mhm.
whatever flux lines we are looking at here, that is stator flux only. And
Stator
from
flux
there we
only.
have understood for that instant what will be the rotor currents, and if those rotor currents is there, what will be the rotor flux direction. The red
Okay. So
arrow mark you can
yeah,
see, but you can see that there is no flux line corresponding to that. So flux lines till
yeah.
now
Now, if you
whatever we
can
have
see it
seen is
here,
only one excitation.
yeah. Now, whatever I can see it here, stator flux is towards this side. Now, north to south, it is going here,
Yes,
and for the
yes,
rotor flux is from the top to bottom. So
yes.
now here we are mentioning, right, rotor flux direction. We are mentioning on what basis it that.
Because we came up with the rotor bar currents. If the stator flux linkages are like this, or the stator flux distribution is like this, then we looked at this instant, at a given instant. So flux lines are like this at a given instant, because finally that is a rotating field. So at this given
Okay.
instant we can calculate what are the induced EMFs, right?
Okay.
We calculated the induced EMFs, and then we took the assumption that rotor bar inductance is negligible compared to rotor bar resistance. So finally if we have to calculate a particular rotor bar current, it will have to be if I do it in phasor terms, then IB, say IB1 will have to be EB1 by ZB1, whatever. This is a phasor, so all these are phasor quantities. AC circuit analysis, basic AC circuit analysis. So this is the IB1. Now for this case, EB1 and IB1, the phases may be little different. If it is a RL circuit, you know that if RL circuit voltage phasor is there, then current phasor will lag it by certain angle. Now we took a realistic assumption that for rotor bar current, because the rotor bar current frequency is very low, or the induced voltage frequencies are very low, so whatever is the rotor frequency, that multiplied by L, that is very low compared to the rotor bar resistance. So this impedance can simply be approximated to be the resistance of the rotor bar, say RB1 in this case. So wherever we had maximum induced EMF at that same the same bar, whichever bar had the maximum flux, maximum induced EMF at that instant, that same bar will have the maximum current also. And if it is positive, it will be positive induced EMF, it will be positive current. So that is why you can see that the pink one in this case, that is bar 19, is having the peak induced EMF. That is why bar 19 I have assigned peak dot current. So
Okay.
the opposite to that, if similar thing is done for some other bar, will have at the given instant you will have negative peak. So that is nothing but this bar. So accordingly we have seen for different bars and we have assigned directions for that. After that, what we have seen is at this given instant of time, all the bars which lie in the on the right hand side are having dot currents, which this bar at 0 degree, that is having peak current, then current magnitude is reducing as we are going both directions. So this is about the rotor bar current on the right hand side, and rotor on the other hand, this left hand side rotor bars are having cross currents. So once we know that for this stator excitation or stator flux bar currents and rotor bar current directions, then using right hand side rule we can see that if this side is cross and this side is a dot, you can place your right hand like this and the thumb will point towards downward direction. That is why we concluded that the rotor flux, if we plot that, that will be in the downward direction. And because of that, if rotor flux is in the downward direction, so from rotor surface it is coming out at this theta equal to 270 degree wherever I am pointing. That is why this side is north pole and this side is south pole.
Okay. Okay.
Now if we try to look at the resultant flux, then we have two magnets, or basically two fields. One field which is something like this, one north pole here, north south pole here, uh, so something like this, and another is vertical. Right, now we have to take resultant of this, because the magnetic field, that is basically a vector. So at all these points, the flux densities will get added vectorially. The flux density due to the stator excitation and the flux density due to rotor excitation. Now what is typically the case is, one flux density, or the strength of one flux density is higher compared to, significantly higher compared to the other. So for an example, if say stator flux density peak is say 1 Tesla, 1.2 Tesla something, then if we actually calculate the rotor bar currents and correspondingly draw the B only for the rotor bar currents, we will see that it is very weak. So it is say very weak like this. Then the resultant will not be at 45 degree, but it will be only a shifted version of the original flux. So earlier you can see that the peak is happening at 0 degree. Now you will see that the peak will happen, it will get shifted in the downward direction. So probably this peak may happen somewhere here, peak may happen somewhere here, and all the everywhere the flux density will be twisted, it will have little twist. So that will be the resultant flux density. But nowhere in any calculation we take the resultant flux density and do any calculation, because if we look at our individual conductors, then if we have a complete turn, then uh, we will see that in the case of DC machine, if we calculate the flux linkage either with the stator field only or the resultant field, it will come out to be the same, because one side whatever addition it will have, another side it will have the same subtraction. So overall flux linkage, that will come out to be the same number. So that is why this assumption is valid. uh, if we try to analyze that, and actually we do not have any other way to do that also analytically.
Thank you.
Is it does that answer your question?
Yeah, yeah, it's okay. Yeah, and one more thing now, the very firstly, now we are showing the directions like see this North Pole and South Pole we are putting on, right? Normally,
Yes.
once if I place it, so for the stator after stator flux linkage formation only. So is there any specifically this side only it has to be north and this side only it has to be south? Is there any specifically we have to how to
No,
identify
no,
that first of all to see that?
no. North pole definition is if there is a surface, if flux lines come out of that, then this surface will be north pole, and if there is a surface where flux lines go into, then that surface will be south pole. At this given instant, we know what is the flux direction. So we know that flux direction is like this. Here it is radially inward, here it is radially outward for the stator. So that is why this surface, this stator surface, flux lines are going into. That is why I have put south pole here. And for this stator surface, flux lines are going out or coming out from this surface. That is why this surface I have put it as north pole. And as it rotates, you can see that this is at t equal to 15 millisecond almost. So at this time instant, flux direction is actually like this downward. So that is why we have to tell this stator surface whatever I indicated, that has to be south pole because flux lines are entering that, and this surface, that has to be north pole because flux lines are leaving from that. Flux lines are leaving from the stator surface. That is how we have uh, uh, named this south pole and north pole, or decided on the south pole and north poles
Okay, okay,
based on the flux line direction.
okay.
Is it okay?
It's okay. Okay. Thank you.
Okay. Any other question at this point of time? Okay. So we started discussing on DC machine. So what happens if we inject DC current into the rotor? So and then if we inject both magnetic fields, then we looked at that the resultant magnetic field, there will be some tilt in that field, and you can look at that here, that the resultant field in the air gap has actually shifted. Earlier the axis, okay, I don't have the figure for that case here. We will see that earlier the axis of the magnetic field was same as the stator field axis when the rotor was not excited. But after rotor has been excited, you can see that rotor rotor, if all these are cross and all these are dot, then rotor flux direction is like this, horizontal. But because of the interaction of the two fields, you can see that at the air gap, the field has shifted little bit on the right hand side, on top. So this is the resultant magnetic field. uh, so you can look at that one side of the stator pole, or this side, the flux has actually increased from whatever the flux was for the case when only stator was excited, and this side, this has got weakened. We'll look at that at, at greater depth as we go forward. uh, so yeah, we can look at that. If two fields are there, then the resultant field in the air gap, that actually shifts a bit, that is not perfectly aligned to any one of the original fields. So we will look at that. Because of the tilt only, there is a torque production, a continuous torque production, and yeah, we'll discuss that. So uh, next what we are going to discuss, next I'll give a brief overview of the things that we will go through next. So DC machine, well, we are well aware of the steady state equivalent circuit model. So we know that uh, we in the armature circuit there will be some induced EMF. So say there is some induced EMF EB, and we know that there are brushes and there are armature winding, there is armature winding, so any winding will have some resistance. So we typically put this Ra, the armature circuit resistance also, and we excite it with this DC voltage, say Va. This is what we inject. This is the equivalent circuit of a DC motor that we often or this is where we start and start reading DC machines. So the equivalent circuit, the governing circuits are like Va, simple KVL. If you apply Va equal to RAIA plus EB, so the torque, that is some constant times Ia, and the induced EMF, that actually depends on speed, so that is again some constant times the mechanical speed, that is omega m. Now if you combine these equations, this equation is often derived that omega m, that is 1 by k into Va minus Ra by k square into Te, because these two constants, k for the torque constant and the back EMF constant, they are actually, they come out to be the same numerically, or the number, the numerical value it has, that comes out to be same, only the units are different. One is Newton meter per ampere and another is volt per radian per second. So only the units are different for this torque constant and back EMF constant, but the value, the numerical value, come out to be the same. So this is the equation that we derive. So if this is plotted, so this, if we plot along the x-axis or y-axis, and Te we plot along the other axis, then this is the equation of a straight line, where this is the intercept, this is the axis intercept. So for different values of armature voltage, these are the motor characteristics. So in this case, the speed omega m has been plotted along the y-axis, and the torque, electromagnetic torque developed by the motor, has been put along the x-axis. So this, in this case we have straight line equation. So this come out to be the y-axis intercept of the straight lines. So Va by k is nothing but this intercept for, say, this is Va, if it is Va equal to 20 volt. So this is the motor characteristic for Va equal to 20 volt, steady state motor characteristic, and this straight line indicates that. And this can be actually shifted, this can be shifted by changing the armature voltage that we are applying across the motor. If we apply say 40 volt, then this intercept, because you can see nothing else changes, only the intercept gets changed. So so it gets intercept, if it was little higher than 500 rpm, it gets little higher than 1000 rpm. So like this we can have different motor characteristics, we can vary the motor characteristics by applying different voltages, and this we can do within the operating limit. So we will always have some maximum applicable armature voltage that we have, and also we will have the maximum speed, or maximum speed we will have, and also based on the the maximum voltage that we'll be able to apply, and based on that there will be some maximum torque that can be generated out of this motor. So this is the steady state characteristics for this, for a motor, for say a given motor with certain resistance, this constants. Yeah, that's all. So these are the electrical parameters. And say how will the operating point. So suppose there is a motor, we give some excitation of say 80 volt. How will the motor know that we at which, or naturally if we keep the motor, where will the motor go, and where will the speed uh, get to steady state, where at which speed will the motor steadily operate at, because initially the motor speed is constant, that is 0, that is at standstill. Now we apply some voltage, where will the motor go? So what will decide that? That will be decided by the what is known as the load characteristics. So a motor that is always connected with some load. So with some couplers, say it is connected with some load. The loads will with just like the motor has torque speed characteristics of its own. Similarly, the load will also have torque speed characteristic of its own. So for the motor, for a given whatever you have discussed, for the motor, if we know what is the voltage that we are applying, and if we know what is the speed for some applied voltage, given a speed, the motor can operate only one operating point, right? Say this speed is told and the applied voltage is this, then the motor will surely operate at this instant only and at this torque only. So because this is the motor characteristic, this red line is the motor characteristic at V at armature voltage of 80 volt. Now next, similarly there is load characteristics also. So given a load, if we operate, if we run the load at a given speed, then that load, the load torque, that the torque demanded by the load will also be fixed. So there is something called load torque speed characteristic. A sample load torque speed characteristic is plotted here, where the load torque is proportional to the speed, proportional to speed square of the speed, which is very typical for a fan type of load. So this is a parabola. uh, uh, this is the point, and this is the parabola, and this is the load torque speed characteristic. Now for a given load characteristic, for a, if we have to run a particular load, and if we have a motor at our disposal, and if we inject or if we apply some voltage across the motor, then we know that by plotting them together, it is possible to decide or possible to determine what will be the operating point. So for a few examples, wherever the load characteristic and the motor characteristic for the given inputs intersect, that is the operating point of that is the steady state operating point of the motor. So for an example, if 80 volt is applied across the motor, then this red line is the motor characteristic, and load characteristic for this case stays is very simple, and it's a single characteristic, it does not change. So wherever they intersect, that is the operating point. That means, what does it mean? If we apply 80 volt to this particular motor and connect this motor with a torque speed characteristic like this, as shown in the left hand side figure, then the motor will operate at about say 2000 rpm while delivering some torque little higher than almost say 44 newton meters. So it will deliver that torque. Now while the motor is rotating at that operating point, if we suppose we think that okay, let us change the armature voltage, let us come down to 40 volt. Now as soon as we change the armature voltage, the motor characteristic shifts. The new motor characteristic becomes this blue one. Now the motor steady state operating point also has to change, because at this operating point, the voltage is an electrical quantity that can be changed instantaneously. As soon as we change something, that armature voltage can be changed. Armature voltage, the voltage applied across the armature changes, but speed is a mechanical quantity, it takes some time to change it. Now from this point, where will it go? Will it go to the, how does it change? So we know from this steady state characteristics that finally it will come back to the intersection point. And in steady state, if we wait for some time for the motor to come into steady state, then it will come and operate at the speed very close to 1000 rpm while delivering this torque, say 15 or 16 newton meter torque. So this will be the new operating speed or new operating point. So our steady state model tells us very accurately that what will be the result or what will be the steady state operating points for a given set of inputs and given a load characteristics. But it does not answer to us how the motor changes, how the motor comes from operating point 1 to operating point 2. So if we plot like this, so say this is the speed of the motor, say this is the torque developed by the motor. Now we do something. Initially it was 0, this was also 0. Then at this say given instant, we do something happens. I'll probably use some other color. So we do something at this instant. Before that it remains at that instant only. And if we wait for some time, we will see that the motor speed actually comes to this say speed omega 1, and it develops some torque say T1. Then again, if we do something else, and it keeps on operating at that instant. And even say after that at some other time instant, say we change the armature voltage. After that, say we so here it was say which we took it to 40 volt. Now here we have taken 40 volt to 80 volt. Now at this instant, if we again wait for some time, then after some time we will see that our speed has increased or decreased, something has happened, and again torque has increased or decreased, something has happened. So steady state, it will reach somewhere that we know, but how does it reach from the initial point to the final point? That cannot be predicted by the steady state equivalent circuit model. Is it very clear? I think it is clear. So the dynamics, if we have to understand the dynamics first, that what actually happens in between in the dynamic condition where the speed is changing and the torque is changing or both are changing, we have to go to a dynamic model of a DC motor or machine in general. So that is why that is where we have to identify the dynamic elements. What do we mean by dynamic elements? So what are static elements? Static elements means if static element, so any element, say in this case we'll just talk about voltages and currents. So say we have some element. If we define the voltage across that element, current is already defined. We do not need the information of any other instance voltage in order to define the current at that instant. So if we know V1 or say VT1, we know IT1 also. We do not need to have the information of say VT to VT0 in order to understand, in order to get to know what is the current at that given instant. So these are called static elements. What is the example of that? A resistance is an example of that, because for the resistance you know IR is VR by R. So if at a given instant you define the voltage across that so there is no dynamic involved in that. So a resistor is a static element. But if you talk about say inductance, what is the governing equation? VL equal to LdIL dt, right? So in order to, if we have to determine IL, then IL is nothing but integration of 1 by L integration of VL dt. So if we have to determine I of t, then we need all the information of the voltages that has been applied from minus infinity to the instant t. with which we are interested. That is the meaning of dynamic elements. So, for inductance is a dynamic element because uh, current at a given instant of time, in order to determine that, only voltage, only the input, that is the voltage information at that instant, is not enough. We need voltage information of that throughout the history. That is what a dynamic element is. So we have to identify the dynamic elements which are present in a DC motor. That is why the field information or the field understanding will be handy when we will try to do that. So we will get to understand that uh, if we have some armature winding, then certainly we'll have some inductance of that winding, and there will be a induced EMF. We'll understand that field field winding inductance also. So we have introduced all the electrical dynamic elements of the system. Now, if we look at the mechanical system, suppose a rotating body is rotating, a body is rotating at some velocity, at some speed, say omega. Now, if you try to at this instant, what is the static coefficient? That is the friction. uh, that is similar to resistance in case of electrical system. So frictional coefficient, if frictional torque, say frictional torque is simply can be put as b omega, then uh, this is like a static thing. If you know omega at a given instant of time, you readily know what is the frictional torque at that given instant of time. So mechanical side, frictional torque or frictional losses, whatever is the coefficient for that, that is a static element. But what is the dynamic element? What is that? That will oppose the rate of oppose the change in speed. Suppose we want to change the speed from omega 1 to omega 2. What is that property that will oppose that? From engineering mechanics or physics, we know that that is called as the moment of inertia. So any body in motion that has certain inertia, that will oppose any change in the speed or rotational speed in case of rotating bodies. So that is the polar moment of inertia for symmetrical rotating bodies. Polar moment of inertia, often written as J. So J is the dynamic element. So the moment of inertia, J is the dynamic element for uh, for mechanical side of the system. Now these differential equations, these are linear differential equations, can be written. So electrical, this armature side, let us forget the field for this moment. Side, say if we apply KVL in this loop, then what we have? We have VA equal to LA DIA dt plus RAIA plus EB. That is a differential equation, and you can look at that, because if we want to go into the steady state from this dynamic case, then because this is a DC motor, so finally this current will be DC. So IA in steady state, it will be capital IA, that is a DC quantity. So at the once we have reached steady state, so DIA dt, that goes to 0. So we have VA equal to IARA plus EP. That is the steady state equation. Similarly, if we try to go to the mechanical dynamic equation, then the electromagnetic torque, that has to be equal to J d omega dt, that is the dynamic part, plus B omega, that is the frictional part, and it has to also overcome the load torque, that is the TL, as a function of omega. What is that? That is basically whatever equation, whatever is this T as a function of omega. So this is the load torque. And similarly, if we suppose we have reached steady state, then omega is equal to some omega, one that is constant, then d omega dt is 0, so this term goes to 0. Then we have reached this steady state term where Te is equal to TL plus b omega, where the motor, if it is running as the motoring mode, then the electromagnetic torque that has to supply the mechanical torque, mechanical load torque, as well as overcome the friction. So that is the understanding about the dynamic equivalent circuit model. So we will discuss that. We will try to understand these inductances from the field uh, understanding that we have developed, or we will going to develop for this DC motor. We will try to have some understanding of the resistances also, relative values, typical relative values, what to expect for a DC machine of a given rating. Then we will also look at the this moment of inertia, frictional coefficient, and these as you can understand, these come out to be the parameters of the dynamic model parameters for a DC machine system. So all these things need to be known in order to so these are known in order to say predict some dynamics. So with these informations known, you will be able to predict that what happens if we suddenly apply some positive voltage. So we suddenly apply some positive voltage. Then with these parameters known for a particular machine, we will be able to predict that what will be the trajectory taken by the speed as well as torque, how much, what will be the trajectory of that, how it will change. Obviously it will be able to tell us that what is going to be the steady state speed or steady state torque, and how much time we would need in order to reach that. So all this information will be uh, available if we know this dynamic, if we include or incorporate these dynamic parameters like inductances, moment of inertia, other things into the equivalent circuit model for a DC machine. So this is one thing. Then next thing, as pointed out probably last class also, for for it is very important to determine these parameters. So we will look at, say, for a given machine. So suppose you are given a motor, a physical motor. How can we do not have anything, we do not have any information of uh, probably any design, or what are the dimensions, nothing, no information we have, but we need these parameters in order to say design some controller for the motor. So how to get those parameters for a given machine, that is the next thing that we will discuss, that is the parameter estimation. What are the important parameters? Important parameters are LA, RA, obviously LF, RF, whose equations are not written here. Now uh, now okay, I have not discussed this interconnection. So we have interconnection of, so I have separately discussed the electrical model, and I have discussed the mechanical model. But in a machine, energy transfer happens from electrical to mechanical. Electrical energy gets converted to mechanical energy, and mechanical energy gets converted to electrical energy. So these two equations are not actually independent. How are they not independent? Because if you look at the electrical side equation, the, so there is a parameter, or there is a variable here, that is EB, the induced EMF, that is actually dependent on on some mechanical quantity. That what is EB? EB is some k times into omega m. So what is omega m? Omega m is the variable in the mechanical differential equation. So this electrical differential equation is disturbed by this mechanical variable of speed. So this term comes as a disturbance to the electrical circuit, or electrical differential equation, electrical model. And similarly, for this mechanical equation, Te, torque, is a mechanical thing. So J is a parameter, mechanical parameter, B is a mechanical parameter, TL is the mechanical load torque. But this load torque, electromagnetic torque, that is decided by, that is scaled by the current, the armature current, by some K. So IA is the variable in the electrical circuit. So some variable in the electrical circuit decides the dynamics of the mechanical subsystem or differential equation, whatever you call it. So some electrical quantity, electrical variable determines or disturbs the mechanical differential equation. So this comes as a disturbance to the mechanical equations. So this is about the interconnection in a electrical machine. Uh, we have to know these interconnections well, because finally we need to, if it is motor, then we need to control some mechanical variables like speed or torque, and load torque basically. We have to change some electrical quantities or electrical variables like the armature current or field current in order to get that. Now that is about the interconnection. Now we were trying to list out the parameters. One parameter we have seen for the, say, let us go step by step. Say armature circuit. Armature circuit has the armature resistance and armature inductance. Now we have the field circuit. Field circuit has the field resistance and field inductance. Now field circuit, say it some current flows. That current will produce some flux. That flux, how this flux, or typically it is also written as flux per pole phi p, that is a function of if, and typically it is a it is a scaling function like this, say kf into if. So this is the relationship between flux per pole and the field current. So this kf is one important parameter that we need to know, how this current, field current, translates to flux per pole. Now next thing is, if we know the current, say, of armature circuit, and if we know the flux per pole, then torque we know is, say, torque, electromagnetic torque is kt into flux per pole into Ia. So kt is the parameter, is the important parameter here. And similarly induced EMF Eb, or back EMF, that is Ke into flux per pole into speed, mechanical speed. So Ke is another parameter that describes any motor. So we need the information of all these parameters for a motor in order to uh, in order to know the dynamic model, dynamic equivalent circuit model. If we want to see the dynamics of that system, then we need all these parameters. So one important exercise that you can do is, you can pick up any DC machines or any drives book in common, or any machine design books also, and you can try to find out what are the typical values. So say pick out one machine of a particular rating, and then pick out, or basically try to see the values of these different parameters, whatever you have listed down: ra, la, rf, lf, kf, kt, ke, and also the mechanical parameters like the j and b. So all these parameters are, you can try to look at the typical values for a given rating or different ratings, or the typical values. That can be one exercise. And then with these parameters we will be able to produce a DC machine model. So we'll be able to produce, be able to have a model of a DC machine. So what do we mean by model? If uh, if we So we have a physical DC machine. What are the inputs through that? We have some terminals coming out of that, say armature terminals, and we have some field terminals coming out of that, and that is the speed of that. And the other side, that is, we have some load. Say we have some load. So what do we mean by model of a DC motor? for a given voltage. So what are the inputs? Inputs are the, we can apply some field voltage, we can apply some armature voltage. For a applied armature voltage and for a applied field voltage, what is going to be the torque and speed of this motor? That, so these are the inputs, va, vf, these are the inputs. Now the outputs are omega and torque. Like, right, this is our DC motor model. And of course, this, in order to decide this omega, we also need the information of the load integrated to this model. So this will also require the load characteristics. So this is the DC machine model that we will develop from scratch. So basically, I'll tell how to. So once these differential equations are known, we will not use the MATLAB. So it is not encouraged to use the MATLAB model of a DC machine. Rather than, so then that is like a black box. We do not know. We are not sure what to do, how it is derived. So we'll understand. We'll step by step understand how to develop a DC machine model for our work, for our own, in order to see that what are the different dynamics. So we will be able to see that what happens if we first give some voltage or field voltage, armature voltage, what happens to these output parameters or output, not parameters, uh, these are the variables which vary with time. Parameters, what do you mean by parameters and variables? Parameters are the ones whose values remain reasonably stable, reasonably same over time, like the inductance value does not change much, resistance value does not change much. All these coefficients that we have found out, like kt, ke, once given a motor, the values remain the same. But what are the variables? Variables are like the voltages, currents, speed, those are the variables. So we will look at the output variables, how they change once we change the input variables. So if we prepare a DC machine model properly, then we will be able to look at that. So that is going to be the next
So
one.
here, yeah,
Yeah.
a small question. So now, whenever I'll apply my armature voltage or input voltage to the my motor, so there is a induction, there is a inductance comes into the picture for a small amount of time. You told, right? So that the inductance will be like throughout all the voltage, like how much ever the voltage I apply, so it will be constant throughout the of my operation.
Yes, inductance value will be constant throughout unless
So
we
that is
go
like
into saturation.
in a dynamic, yeah, actually, until it goes to the saturation. But as like for a very small amount of time only, it will be there again. Once it goes to the steady state, that value will become zero. Also,
No,
we
no, inductance
discussed,
remains
right?
the same. Inductance value does not goes to zero. This is say
Okay,
RL.
okay,
Inductance remains as it is. The value does not go to zero. The voltage across the inductance goes to zero once it reaches steady state. If it is IA, then till the time IA varies, there will be some LA, DIA, DT. That is the voltage across this inductance.
okay,
Till the time there is some change in IA, the voltage will also appear. If IA becomes a DC, then dia dt is 0. So the voltage across the inductor becomes 0. So this effectively becomes short. It is not that the inductance value is becoming 0. It is that the voltage across the inductance is becoming 0. So we need not consider
okay.
that in steady state.
Okay. And if I can consider for the BLDC model, brushless DC motor, we do not have a term called VF, right? So just I can go with the VA term alone.
Yes, yes. We have three phases. So
Yeah,
three
we
phase
again three.
VR, VY, VB will be there.
Yes, 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 yes. If possible, like after completion of this course, like we can just brush up with the BLDC also. Like
Let's see whether we have enough time
oh,
or not.
yeah.
So the idea is, if we understand one well, then we can uh, get to understand others also. So we'll try to understand one first, one motor well, the end to end of
Yes.
one motor. Then it is possible to understand everything.
So directly now we are going to the modeling of again power electronics. Everything is come. So we are not detailedly discussing about the DC machines like how armature reaction that and
No,
all
no,
will
we
comes into the
will
picture
discuss
right now.
that. I'm just giving an overview of what are the next things going to be there.
Okay.
So next, after that, once we have developed a model for the DC motor, then we will look at what type of power electronic converter is suitable for. So it's a we will look at some converter. We will have DC. We will have a DC voltage only, some DC voltage input, and it would require DC voltage output. Now we will look at uh, what is going to be the converter for that, or what should be what switch configurations we should use. So this whether a buck converter, a simple buck converter, is suitable to run a DC machine. If yes, why? Or if no, why it is not, and why, how we can modify the well-known buck converter in order to for running a DC motor, which is basically an active load, and what modifications are needed in that. We will briefly, or we will discuss upon that. And after that we will have a model, or a power electronic converter also in the model. So a power electronic converter will be sitting, and we will change this voltage, armature voltage, through a power electronic converter. So we will give some input to the DC voltage input to that, and power electronic converter will give the armature voltage, and we will change the duty ratio of the switches in order to change the armature voltage. That is the next step, that will be the next part of what we are going to do. And after that, so what is the system, so what will it look like? We have a model of a DC machine. It has certain inputs like VA and VF are the inputs. For cases, we will keep it, we will just apply some rated value to it, and will not bother it. It can also be bothered, but for the purpose we will not bother. We will not change the field voltage. Now these are the output variables. Now the next step that we try to do is we will feed the DC motor with some power electronic converter, which the input will be some duty ratio, and another input is the DC link voltage, or the input voltage of this DC to DC converter. So we will try to change the armature voltage by varying this duty ratio instead of directly varying the armature voltage. Then we will then this is the next level. Then we will try to look at, suppose we are giving some speed reference, and we have this speed. We can sense this, we can sense it. So this becomes our sensor gain, and we can sense this speed, and we can feed it back. So we can have some kind of system like this, where there will be some controller which will give this duty ratio as the output. Now we will try to see how to design this controller in order for proper current control and speed control. That will be the next objective that we will eventually realize. And then we will also try to, so this is the first cut controller design. Next we will try to see what happens, what are the physical uh, challenges that we may face. So typically it is well known that suppose we design some controller parameters, we design for that, and if we apply that same thing, it does not work, or it does not work to satisfactory level. We will try to understand or investigate into the non-idealities, or uh, the things that we have not considered in our during our controller design, which may cause this, and we will try to understand them, we will try to incorporate them, and then redesign our controller, so that whatever controller parameters we will design, that same thing, because we have modeled our system reasonably well, so that same thing will work. only the reason it does not work is because we have not modeled our whole system accurate enough. Or I'll take into this also. We have not modeled our entire system accurately enough. That is why there may be some differences, or there is a need to tune it. But actually, if you design well, then there is no need to tune. Whatever you design, that will work. And final realization will be a closed loop speed controlled DC to DC converter fed DC machine. That is the final uh, objective that this course will uh, reach to take all of us to. And we will, so final objective for all of you is to be able to do a simulation in MATLAB Simulink, going step by step. First, making a model of a DC motor, making a model of a power electronic converter, then seeing the dynamics, how to design a controller, incorporate the non-ideal redesign, and it will work. So that is the final introduction, the long introduction to this course, which eventually became longer because I chose to discuss a bit of fields for different machines also, not only the DC machine. So it got elongated. So yeah, I think it has given us a good enough uh, basis to go to the next steps and understand the whole thing reasonably well. Yeah, so I'll close today now. It has been a reasonably
Yeah,
long lecture.
thank you, Samrat. All the valuable information from the basic and from the scratch level we have covered as so far now.
Yeah,
Yeah, it's very privileged. We were attending and then we are gaining the basic knowledge. Actually, we have studied it and we are like in my case, I am just telling. So now like some dots, like everything we have connected now. It's very an honor actually. And especially, I just wanted to discuss about some application. Like, if you are free sometime, just I'll give you a call. Like, if you don't mind. So, if you are like, there is some application related to I wanted to discuss. Yeah, we'll discuss in a call. It will be better, I feel. That
sure.
is also
You
like,
can yeah. Go on.
yeah, yeah, yeah. Like, if you are okay, like to go ahead with that. So brief discussion about myself also given a call only.
Okay, let's see. I'm quite caught up now, having multiple
Hello.
deadlines. So if
Yeah,
I
yeah. That's what
get
like.
over that, and then probably we can discuss. But at this point of time, it may not be possible.
Yeah, yeah, not now, not at this point of time. Like, you just like, if you can give me some time so that I can bring that points to you, like based on that, we can have further discussion actually.
Sure. If you have something, you can message always. I will try
Okay,
to
yeah,
look at it, and
yeah.
then we'll
Okay,
discuss.
I'll text you first in a WhatsApp.
Yeah.
Based
Great.
on that, we'll discuss. Okay, thank you.
Okay.
So I
Is there
have
any other
some
question?
doubt. Yeah,
Okay.
I have a few questions.
Yes.
Suppose the motor is a free running motor. The load is not connected.
Okay.
How does the torque speed curve of the load that case will look like? Is it just a flat line or a,
No, it will be if it is a free rotating motor. Say this is a motor. Say this is a motor, and it has shaft all over. So there is a rotor, right? Rotor is there, and that has some shaft. Only thing is shaft is not coupled to any load, and it is rotating. Now you understand that if you rotate at lower speed, the friction will be lower. If you rotate at higher speed, the friction will be higher. Simple aerodynamic friction. Because of friction with air, there will be some friction, and typically that is a fan load. Whatever fan load is, the fan load is those things where you are the purpose is to push some air into that, basically some compressor kind of a thing. So there, your intention is to push some air, and finally this fan load type of thing, that becomes a load torque characteristic. If it is a free running motor, still it is like a fan load only, because finally something is rotating, and some aerodynamic friction it has to overcome. So it will be this fan load type only. Only thing is the value will be very low. So it will be
Okay,
something
sir.
like this, quite low, or I think I have done it wrongly. This is vertical is wrong speed and this is low torque, so it should be the opposite way.
Okay.
It will be very
So,
low torque for higher, very low torque, but it can go to higher and higher speeds. So as the speed increases, then the torque will also increase exponentially like this,
so,
or quadratic nature. Yeah.
so in the resultant flux density case, that discussion is over or something is bending. We have seen
Which
rotor
one?
wheels in the last APM photograph we have shown
No,
that
no.
there
We
are
will
two
discuss.
fields.
We will go to the field of DC machine next. After that only these parameters will come up and we will go to the other portions. So still
Okay, so
we have not discussed the field of the DC machine properly.
okay, so the resultant flux density flux is actually depends upon the how much is the
Load.
armature flux.
Yes.
Okay, the load. Then the how the inductance will remain constant throughout the range because it is in the diagram you have shown the machine is kind of unsymmetric. There are space where air gap is very high. Some
Hmm.
places air gap is very low. Then how the inductance will remain constant irrespective of the load current.
Okay, we will discuss this when we discuss about the inductance. So basically, this is a topic. So we will understand what do we mean by inductance or how to understand the inductance from the field. So when we discuss that, that will be clear.
Okay, okay, sir. And will you also take care of the permanent magnet DC type of motor? Other than if we don't have a field winding, only permanent magnet sitting on the stator.
So let's see
In
what we are, whatever I have discussed. There I have kept the field to be constant, right? In this case, I
yes,
have
yes,
assumed that in this case, we have two choices. Either we can give some DC supply to the field, or we can assume that we are injecting the rated IF, and that will create the rated flux per pole.
yes, yes.
So in case of permanent magnet motor, nothing will change. Only the flux per pole will be remaining constant throughout. Nothing
So
else
the
changes for the PMDC motor other
so
than
the
that.
parameter estimation will give all the values.
Yes, yes. For
Okay, okay.
PMSM, we need not get, because there is nothing called field inductance or field resistance. So these parameters will not be there, and there is nothing called field current, or function of field current that comes out to be the flux per pole. There is no such thing like this, like the KF into IF that I have discussed. This KF is also not present. So these three parameters will not be there for PMDC motors, but all other parameters will be there. And yeah, uh, we can discuss that how to, basically that remains the same, how to get the parameters for that. So
Okay,
if
sir.
we have a electrically excited field, then we have this additional three parameters along with the other parameters.
So will you please cover position control also one more loop other than speed control?
Yeah, position control.
Uh,
If it is, yeah, if speed control is done, position control also can be done.
okay, sir. So we are also going to go through the numerical simulation. How to
Yeah,
do the numerical simulation?
I'll indicate that. I'm not sure whether I'll be doing that online or not during classes, but I will show you all the steps how to do that and probably show you the results of that. So uh, it is uh, so all of you are encouraged to, today I have told that for a DC machine, look at the different parameters. So this you can start as the first exercise. Take out any DC motor and look at the parameters, list down them. Then when we discuss that how to build the dynamic model for a DC machine, so you can basically make that and enter all your parameter values, and then when we discuss, I will discuss all the details. Only thing, I may not do it live in the in this thing, like I will not open Simulink and make block by block, that I may not do.
Okay, okay, sir.
But all the important details will be covered. With that, you will all of you will be able to build that.
Okay, sir. If the model of the motor is available and we don't need to do any tuning, right?
Model of the motor is available means?
The parameters of the motors are available, then we don't need to go for the tuning. We can directly design the controller, right?
Yeah, but
Yeah.
in the actual case, there will be always some error in the parameter estimation. Suppose we estimate that it is say 1.2 Henry or 1.2 millihenry in of the armature inductance, but it may not be that. There may be some calculation error or estimation errors. It may be 1.3 millihenry also. So why this parameter or this tuning is needed? Because of these uncertainties in the parameters estimated. So we will look at a robust controller design that will be able to take care of all these parameter variations and still uh, deliver the uh, desired results.
Okay. Okay, sir.
Okay. So shall we call it a day? Sure. Okay. Thank you.